this talk is meant for sort of general audience. And what I'm doing here is it's something that we've been thinking about with my co-authors in terms of really generalizing some concepts and maybe creating a survey. And I'm trying out different ways of generalizing these concepts. And it's really great to get input from a variety of communities. And here's the statistics and random matrix communities are definitely a very good fit for. So this is about classifying randomness, but not really specifically in deep neural networks, but in whatever optimization algorithms we need. So I'll set up like a MERT. I'll set up the notation. Like MERT, I use x as a variable. I will stick to my notation. Moreover, n is the dimension. Little n is the dimension, not d. So please be mindful of that. And so what is an oracle? Like, what are we even talking about? So there are many different kind of understand. We all kind of know what an oracle is, but defining it clearly may depend on the person. So what I'm trying to think about is let's say I'm writing an algorithm and I'm writing a code, and you're the user, and we have to have a handshake with you about what kind of information you're going to give me, right? Now, I'm going to divert from that a little bit because at some point I will start creating these oracles myself, but still, the idea is that some way, so my algorithm will need to ask for something, and then some implementation code, whatever, will have to give it. And we'll have to agree on what that thing is. Okay, so that is an oracle. So the most kind of obvious oracle that we all use in optimization is the gradient, right? So if you want to optimize, it is very hard to optimize without the gradient information. So the classical one is I have x, oracle gives me gradient, I make a step, right? I make a step of some size. This is my step size, alpha k. And if my functions, for example, are L Lipschitz, well, sorry, it should be L smooth, actually. No, the gradient is L Lipschitz, correct. OK, gradient is L Lipschitz. Then I know that if I pick my step size sufficiently small, that is 1 over L, then in every step of this method, my function value will decrease by the certain amount that is proportional to the gradient. This should be xk. And therefore, I can devise all kinds of convergence rates. If my f is convex, then it's one thing. If it's not, it's another thing. But the point is that this is the inequality that kind of drives it, right? I get this improvement. OK. I can also have something that is not the gradient exactly. I can have a descent direction. So gk can be a direction of descent of sufficient size. And this inequality is kind of what we want for some kind of fixed data. And then in this case, we again know that if I pick alpha less than this theta over L, then again I have this improvement. This alpha, well, it's still alpha here, but notice that if my theta is small, which means that my g and my gradient are more orthogonal to each other, then I have to take smaller steps, right? So this is the first glimpse of the fact that whatever we get from the oracle, which gives us the direction in which we're going to go. I might not compute the gradient, but I somehow compute gk, dictates what kind of progress I can make. Now, there are a whole bunch of questions about how do I know, how to pick alpha k, blah, blah, blah. I'm not going to talk about it here. My whole point is, if we put strict rules on the oracles, we can say what kind of algorithms progress in what sense. OK? All right, so for example, now I have an oracle. It's inexact oracle. It computes g instead of the gradient. I can have the following bound on the error. This bound has 2 terms. And this is going to be important because I'll use that a lot. 2 terms. One is the constant noise. The other one is a variable noise, or what do you call relative noise, right? And the absolute noise. There are many terms to that. So now there are 2 regimes. If my constant noise is 0, so I only have relative noise, Then if I pick this MV smaller than 1, then I can show that my G is the descent direction, and this is a complicated formula for what alpha k should be, but you can see that MV has to be less than 1, otherwise it wouldn't work. And then I can pick alpha k, and again I have this improvement. Great, okay? So this has been explored in deterministic optimization forever, actually, these kind of things, and it's known as a, if MC is 0 and MV is less than 1, it's known as a norm condition, and I think it exists in like papers from 1960s maybe even, or at least 1980s. If MV is equal to 0, we just have a bounded noise, deterministic bounded noise on the gradient, and we can't converge to an optimal solution, obviously, because we're never going to get gradient to 0. But you can again see what kind of improvement you're getting here. And as long as basically, so this is my step size, alpha k times the length of the actual length of the step, right? And so if that piece here is not, so this is what I'm getting as improvement, and this is what I'm losing on every step, possibly. And if this is smaller than this, then I'm fine, right? I'm gaining something. When is this smaller than this one? This is smaller than the gradient norm, right? So this kind of can see that you can basically detect where you're going to converge. That you converge to some kind of neighborhood of a solution that's dictated by this noise MV, the constant term. Okay. All right. We care about stochastic oracles, right? So let's see what we can say in stochastic oracles. So now I have a stochastic oracle. G is some kind of a random vector. There's this oracle cost that I'll talk about later, because that, it would be interesting to check it out. But right now, this is just notation. And I'm, again, taking the gradient steps, or so to speak, the steps with this gradient direction. OK, so what am I going to assume? So these are relatively general assumptions, but they're not the only assumptions. And that's kind of where the interesting things happen. Let's assume this sort of setting. So my gradient, stochastic gradient, may have a bias. Now, most people here were talking about cases when there's no bias. And very often we can assume that there's no bias. But so we'll assume, we'll look at, so the bias is MB. If it's 0, then there's no bias. Great. Then there is this variance bound, which is MC plus MV. So again, we have a constant noise, but now it's the bound on the variance, right? So there's a bias, which is undiminishable noise. And then there's this variance, right? So it has the constant term and the variable term. OK, so MC, MV. All right. The key inequality that, before we had what happens to the, on every iteration. This is, again, what happens on every iteration. But now it's an expectation, because we have random situation. And, you kind of assemble the terms. And again, you get what? You get this. This is negative. You want this to be negative. So if you pick alpha k small enough, this will be negative. Then there is this term, which is positive. That's not good. And there is this term that's positive. OK, so if MC is 0, and if MB is 0, then I only have this term. And then as long as I pick alpha k smaller than which is right here, if alpha k is smaller than 1 over LMV plus 1, then I can have deterministic rate of convergence. It's basically the same thing as a deterministic algorithm, just a little bit shorter steps. So my steps are basically 1 over L times whatever that constant is. OK. So that is, these things, are known. They've been written up. So if MC is positive, but MB is still 0, then I don't have this term, but I have this term. Or it doesn't matter what MB is, but I still have this term. This term is going to hurt me as long as it is basically, so I mean, this is, everybody knows this. So if I manage to basically pick up alpha k, so here I can pick alpha k constant, but here I have to start diminishing it so that this sum is finite, so that the damage that I do on every iteration eventually is finite. and then this will dominate, and then I will converge somewhere, right? We know that. Finally, the MB term is exactly the same as before. It only matters as long as this term here is somehow worse than this term here. As long as it's smaller, that doesn't matter. So we will not converge to an optimal, to the stationary point, but we will converge to somewhere where the gradient is sufficiently small, depending what the bias is, right? There are, I'll show you cases where you can actually drive the bias to 0 at some cost, but this is, kind of the idea. So as long as we characterize how the noise looks, we know what to expect from an algorithm in some sense. OK, so let's, for example, see, it's a very basic idea, just, from the point of view of expected risk minimization, what is it that we get? So if we have, so I'm optimizing the expected loss. And if we have, if we have the, this behavior for each loss function, so basically in expectation, the variance has these two terms, the constant and the variable noise. Then I take a batch size B, I average out the gradients, I get my gradient estimation, right, the usual way. It's going to be an unbiased estimator, and its variance is going to be like this. So my MC is going to be proportional to 1 over the size of the batch. Oh, sorry, this should be the sigma V, not sigma C. And what are my points then? So there's a lot of work recently, for example, in assuming that MC is 0, or sigma C is 0. It's known as interpolation conditions, strong growth condition, whatever, and somehow there's a belief that at least in neural networks it really holds, over-parameterized, blah, blah, blah. And you basically can see that right away that you would expect the algorithm to behave as if it's a deterministic algorithm. So the fact that you have a stochastic gradient only matters in the sense that you will select a smaller step size. Everything else is going to be the same as deterministic algorithm. So it is important. You can see it, from this kind of analysis. So as soon as you're just saying my MC is 0, then I have all these nice rates of convergence. OK. Also, what you can see is that it does not make any difference what batch size you pick. Under the assumption, which is not what Courtney is doing, clearly, that flops are time, or whatever you want to call it. So what I'm saying is that if you pick B to be 1,000, right, then your MV, MV, right, MC is 0. MV is 1,000 times smaller, but your step size is 1,000 times shorter. So you'll make 1,000 times more iterations. You can see it from this very easily, OK? So under the assumption that whatever batch size you pick is just translates directly to flops or computation or whatever you want, then it does not matter what you pick as a batch size. Now, we all know that it does matter. But that's probably because you should really consider what is the cost of your oracle and how it depends on the batch size from the point of view of the hardware you're using, the implementation, cache memory, whatever, right? But it's not as simple as just the actual computations from mathematical point of view, OK? All right. OK, so let's shift gears and move away from neural networks. And where else do these oracles come from? I told you my title is Where to Find the Stochastic Oracles. So let's look for them in other places. So here I'm going to talk about approximating gradients and projected gradients in subspaces. So the regime is, and first I'll introduce something that doesn't make sense computationally very much, but then I'll explain where it does. So I have a million dimensions, and I'm going to generate random vectors, and I'm going to generate big N of them. And to specifically confuse you, big N is much smaller than little n. So big N is like 10. Right. So I can pick my vectors as Gaussian. I can pick my vectors as unit on a sphere. I can pick them as random coordinate directions or random perturbed coordinates. So basically the Haar matrix, right? Random orthogonal directions. So these are the 4 I'm looking at. If you have other ideas, I'm really happy to listen to those. This is the right community for that. So, and I'm going to compute my stochastic gradient this way. So I'm going to project the gradient onto each directions. Then I'm going to sum this up with some constants depending on my situation, and times these directions, right? So what I'm going to get is a vector lying in the subspace generated by these random directions. And here are the bounds. So this is a stochastic gradient. All of 4 are unbiased. All 4 do not have any constant term in variance. It's only variable noise. And this is what it looks like. So in the first 2, they're very similar. They're like tiny difference here. These are the Gaussian and the sphere directions. So that's basically your MV, right? So what is interesting here, again, your MV is directly inversely proportional to the number of directions you generated. So you do more work, you generate more directions, your MV goes down. So whatever stochastic gradient algorithm is using it is going to make larger steps. So again, the trade-off is exactly like in the previous case, very, it's, in some sense non-existent, doesn't matter in theory. In practice, it matters. These 2 are better in some sense. They're always better than this when you think about it, because first of all, so these don't generate projection of the gradient. They just generate some approximation of the gradient projection onto the random subspace. These, because you're basically computing this with orthogonal directions, they actually generate a projection of your gradient onto the space. So first of all, if the number of directions you generated is actually little n, so if you create a full subspace, you have computed the correct gradient. There's no question about it. So that's why there's a max between this and 0. So as soon as big N is as large as little n, this disappears, and there's no error at all. There's no longer stochastic gradient here in both cases. And it's better because there's a big N here instead of 1, right? So these are always smaller than these. On the other hand, when your little n is huge and your small n, little n is huge and big N is small, then these are pretty much the same. And the difference between these basically methods is that you have to generate orthogonal directions, so sometimes it just costs you linear algebra, but other than that, it's not that different. Okay, so why would we be doing this weird thing as projecting gradients onto random directions? Well, we won't unless it's coordinate directions, which case it might be easier to compute the gradient, just gradient for one variable. But it is really useful when you don't have any gradient information and you're actually using your first order, you're using your 0th order information, the function values, to approximate the gradient information. So here we're in this derivative-free setting where you have access, and this is a whole other conversation how we talk about 0th order oracles, but I'll assume something kind of basic. I'll assume I have a stochastic function approximation. So my true function is phi. I compute the stochastic approximation of it. I'll just bound its variance at some point. So I have function values that I can compute. I cannot compute any gradient information. What can I do? I can compute an approximation of the directional derivative. So I pick a random direction u, and I take a finite difference. And here it is, right? So this is the finite difference. And because this is random, right, I split it up into 2 pieces. And this piece is basically the finite difference approximation of the true projected gradient, a true directional derivative. And this is the noise. And this delta here, it's not probability. It is just the step size, right? So the smaller the delta, the better this approximation is. The smaller the delta, the worse this is, as we'll see in a second. So it's forward differences with error. It's nothing terribly new here. So if I assume that my error in the function values is bounded by just some, well, the variance of the error is bounded by sigma, then again, splitting this thing into two pieces, I'm going to look at the error between the finite difference approximation and the projected gradient. And there will be two parts here, right? So this part is bias, because this comes from the fact that instead of a gradient, I'm computing finite difference. So there's always that bias. It just comes from finite difference. The thing, it's going to be, you know, like this in deterministic optimization, deterministic setting as well. This comes from the noise. So now, what does it mean? So if I had exact function values, I don't have this term. My sigma is 0. I have deterministic function values, computed exactly. I don't have this. But that means that I can make this bias as small as I want. But if I have noise, which we always do in computation, right? It's well known if you're doing finite differences, you don't pick this delta less than 10 to minus 8, because your error is always 10 to minus 16. It's the same thing, but just now scaled with whatever error that exists in your function value. So you cannot pick this delta basically too small, because this term will blow up. If you pick it too large, this term will blow up. So you basically want a square root of sigma. I think it should be, yes, sigma, right. It's sigma, it's not sigma squared, right. OK. So now we put this all together, because we learn how we'll approximate the directional derivatives. We also know how directional derivatives approximate our gradients. So we can have a theorem about this with MB, MV, MC, and MV, right? So now we have a stochastic gradient situation. And then this MB here is the square, whatever. This is Lipschitz constant. This is the step size, the square root of dimension. This is MC. And MV, as before, comes from the fact that we're approximating a gradient by projecting it onto a random subspace. So it is immediately clear that why we would want to have big N to be small, because big N, it's here, right? So our G is computed as the sum of these finite difference things for big N dimensions. So if we have 10 dimensions, I'm going to compute one function value at x and 10 of them at these directions. So I have 11 function values to compute. 11 function values, and I approximate my gradient to some degree. If my dimension is 1,000,000, it sounds like a big saving. But there's no free lunch, because I can compute instead of 10 directions, I can compute 1,000 directions. What would it buy me? It will buy me a smaller MV, and in principle allow me to take larger steps, and I'll have fewer iterations. So without this kick in from these constants, it really does not make any sense. Rather, it does not make a difference in theory if my big N is large or small. If MB and MC are large, then this maybe makes less important contribution, and then you're doing something else, which I'll tell you in a second. I just want to say that these are very basic statements, and they're not correct in reality. In a sense, for example, if you have larger big N, right, and you have a more accurate gradient approximation, you can do things. You can do quasi-Newton methods. You can do other stuff, which speeds up your practical algorithm significantly. So there are definitely things to consider, but they cannot be easily seen. What we can see here in this kind of analysis is, in some sense, just because your method has cheaper iteration doesn't mean it's a better method, basically, in this case, right? But again, if these terms are bigger, then it does make sense to have probably a cheaper method, because there's nothing you can, you cannot pick a constant step size. You have to diminish it anyway, and then things work differently. OK, so here is, for example, a fairly standard approach in simulation optimization, where they have a lot of this kind of situations. So you have this bound, and then, for example, and then these are the terms, right? And so you're trying now to, you can try, so this is bias. It prevents you from converging. If you want to converge, you can drive delta to 0. If delta goes to 0, then your MC is going to explode. But then, if you remember, the way we dealt with MC term is by driving alpha to 0 fast enough. We can actually do the same thing here, but now this time this is the difference, that you have to really drive it fast enough compared to delta. So you're doing basically some kind of a game there by driving bias to 0 slower than you're driving the step sizes to 0, and then you can actually converge. Yeah, I'm not getting into details of this, but just an idea. OK, I forgot when I started.
You have another 15 minutes.
OK, good. OK, so now I'm going to switch gears and talk about other type of oracles, which I find more fascinating. But I mean, they're still stochastic oracles, but the assumptions are different. And this is where we're still working on what exactly we want to say. So, OK. So basically, the difference here so far is that now I'm going to talk about not the gradient oracle anymore, but much more generic oracle. So it's generic oracle of something. I want to compute some quantity, phi of x. I want it to be computed. I'm shaking hands with you. You're going to provide me with its approximation. I'll still call it g. But this no longer is necessarily the gradient. It's something. And we'll see examples. And I want, in some sense, a bound on how close they are. And again, very generically, I'm using a norm, but it can be something else. And the probability of that difference being bounded in some way has to be at least p. Otherwise, I don't know. Right? So it's a much more loose statement for the oracle, in a sense that I want some bound to be enforced with a given probability. Otherwise, I'm not asking for anything. This is much harder to work with this oracle in principle, but people have done it and have produced good results. So it is a very valid thing to look at. And also, yeah, it allows for interesting other things. OK, so I'm going to give 3 examples. The first one is actually from a while ago. And this is kind of what made me work on these sort of things for the last 10 years. It's very neat and simple, but I'm not going to give you great details. So we used to work in this area of derivative-free optimization, where you build models of your objective function by polynomial interpolation. So you don't have gradients or Hessians or whatever, but you build interpolating models, basically second-order polynomials. And they work very well in many applications. Right, so if you have dimension n, little n, the number of sample points, the interpolation points that you need to construct a quadratic model is n squared. It's n squared over 2, roughly, right? So it's a lot. It's a lot to expect to compute function values at n squared over 2 points. There are ways to deal with it, and they've been done. But then we had this one simple idea that what if your Hessian is actually sparse? It translates very easily to sparse gradients, but I think it's just less common to have sparse gradients. And Hessian is sparse. Moreover, it's kind of approximately sparse. And the sparsity pattern actually may change as your algorithm moves. So you need to figure out that sparse Hessian, but you assume it's sparse. What do you do? And everything is obvious, except for it's a lot of nasty kind of math there, but I mean, the result involves RIP properties of random matrices, except for they're not Gaussian matrices, they're much more complicated matrices. But the whole thing comes from the fact that I'm basically taking a certain number of directions again. I take a radius delta, I compute, this is my interpolation set. I compute function values of that set. Sorry, there should be phi actually. Well, if you have accurate approximation. We were considering deterministic functions. And then I construct the quadratic model with the through interpolation. But I construct it by using compressed sensing, basically. So I'm doing sparse recovery. I will not go into details of this. What is the point? I have to pick the directions randomly. They have to be chosen randomly according to certain distribution. That distribution is a little complicated. I have to pick enough of them, and enough of them is this. So if S is my sparsity, then the number of samples needs to be something like this. And this is better than n squared when n is large, right, significantly. And the whole point is that, sorry, this should be the Hessian, not the gradient. If Hessian is approximately sparse and I sample enough sample points and these are random, then my Hessian approximation, which is random, so this is an oracle for the Hessian. I'm asking Hessian to be computed. I get some matrix, which is recovered by doing some kind of linear programming problem. So there's some complicated, not very complicated approximation going on. And what I get is the oracle. And this oracle satisfies this bound with this probability. And I'm not putting the constants here. There are a bunch of constants involved. But basically, the error between the Hessian approximation and the true Hessian is bounded by the radius of sampling. So if I make this radius smaller, I can make this error arbitrarily small if I want to. So I can approximate my Hessian as well as I want, but only with certain probability. And given the tools involved, I don't know if I can bound the variance of this Hessian. It sounds complicated. Maybe somebody here can do it, but we certainly couldn't. So this is the kind of oracle we had to work with. Like, we don't know what happens with this, with probability 1 minus p. Now, you can do convergence analysis in a simple form, and many, many people have done it. If you assume that something good happens with probability p, you're just going to assume that it's going to happen on each iteration of your algorithm until you stop. You can do that, and that's a valid thing to do. But you can actually do better in many cases. You can actually prove, and I'll just quickly list papers at some point. OK, another setting, robust gradient estimation. So there are very, very, very different types of robust gradient estimations. I'm just going to give one example just because I'm kind of thinking about this. So again, I have the expected risk minimization. I have the gradient of each individual loss function for each particular d as bounded. Well, this has to be expectation over d. I don't know what happened with that expectation. There was supposed to be expectation over d here, but it's bounded again. Oh, no, sorry. Here it's not an expectation. I actually assume that it happens just for simplicity. I assume that this is true for every d. Otherwise, I have to have more random variables involved in this derivation. So for every data point, I assume that this holds. So some kind of bound that I want. OK, but I will corrupt this gradient. So basically, I'm going to take this gradient as is with probability bigger than half. OK, that's definitely an error. It should be bigger than half. And with otherwise, I'll corrupt it. So either I keep it or I corrupt it, right? And here's the picture, right? So blue here are the 3 nice gradients, and light blue here, you probably don't see it very well, are the corrupted gradients. So if I average them out, I get bad things. In this situation, it's not terribly bad, but you can imagine high dimension, whatever, you'll get really bad situation. So what do? One of the standard things is doing geometric median. So what does geometric median do? That's the computation. You basically take in the argmin of these GIs that you're given. Some of them are corrupt, some of them are not. You compute you compute the vector that minimizes the distances to all these vectors. It's an optimization problem, but it's not very hard. So you compute that. And then what do you know about the result? What you know is that if more than half the vectors satisfy these bounds, if more than half do, then your geometric median satisfies this bound with some constant, times some constant. So it's this bound times a constant. OK? And if not, then you don't have it, basically, right? So here is kind of like roughly written result, which basically says that the probability with which this geometric median is sufficiently accurate with respect to the gradient, there's this bound here, blah, 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 is the same as the probability basically of this binomial variable, which is the number of corrupted gradients, is less than half. That probability is easy to compute, right? Easy to write down. Yeah.
Xi is binomial, but how is it reflecting?
So Xi is the number of corrupted gradients.
Okay.
Yeah, that, right. Yeah. I mean, it should be, OK, I think I'm overloading the notation here. Here, Xi should be not the number of corrupted gradients, but the actual 0, 1 outputs of corruption. And here it is the number of corrupted gradients. Yeah.
Does it matter what the corruptions are exactly?
If I can say something about corruptions, I can probably say more about this, for sure. Yeah. Here I'm not saying anything, so I don't know. Right. So this is very generic, exactly. Because, I mean, we were talking about this a little bit earlier in this workshop, like what are the interesting corruptions really, right? I mean, where do they come from? Like that's a whole other thing. That's interesting stuff.
So is there a way to, for example, avoid the optimization problem without taking geometric mean, maybe doing some sort of clipping or?
So very interesting. I actually have been working with undergrads on this. So we're very slowly progressing. But so Dima Druzhyatsky suggested a different method, which does basically pairwise comparison and picks something with like the smallest radius that contains more than n+1 points. So you don't do optimization. Right. It does not seem to work as well. We're trying to figure out why. Now, the geometric median is indeed, like, it took us forever to even figure out that we were using mosaic, and it was terrible on like a large scale problem. But actually, there's this Weizfeld algorithm, which is really fast. And so even though you do have an optimization problem, it seems to work really well. And we were looking at the setting where the dimension is very large, but the number of gradients is not. So we're looking in this Byzantine machine setting where you really have just a few. So you have 2 corrupt gradients and 3 uncorrupt ones. But the dimension was like 500,000 or something.
I think for every dimension, if you sort them and then use the sorted, then maybe it may potentially work. But of course, one has to try it. I don't know about sorting. Maybe a good strategy.
But it's still so. The point is, like, if you don't do geometric median, you will pick one of them. And I still don't know the statistics exactly of geometric median, but there are some interesting results in general. But it's yeah. Anyway, it's something. Because I think they have better property. If you have geometric median has somewhat better property than just one of the vectors. But
maybe
I don't know.
More robust statistics. And
yes, exactly. Right. It seems like, but okay. Finally, this is just because Michael was here, but he's no longer here. So, but it's one of the very good examples of another probabilistic oracles. It's from their paper with Fred Rusta from a few years back. Where they do subsample Newton method, and so basically they just take the Hessian from I think in their case, it's a positive, it's a convex problem. They subsample the Hessian, basically the same thing as we did before, but now with the computing the Hessian, not just the gradient, but with a mini batch. And then in their paper, I just took it directly from there. They have a statement about how many samples you need and what kind of approximation you get, this time not in the Hessian itself, but in the smallest eigenvalue, because that's what you're interested in if you're trying to do some kind of convergence result, right? So again, so the result they have is like if you sample enough, you get this inequality. So you have a oracle, and you have the inequality for this oracle with certain probability, and then they just assume that it happens on every iteration and everything works beautifully. All right. Okay, how much time do I have?
We're at time.
We're at time. Okay. Then I'll just wrap it up. So there are interesting ways to compare different type of these sort of oracles, and what is you assume about them. So I will leave it to other discussions. This is a picturesque comparison, and what my point is that these kind of oracles have been used in the literature. And this is, for example, for analysis of stochastic trust region methods has been used in these papers. And we call it step search now because it's not line search, but it's basically line search. One of the papers is with Courtney on using this sort of oracles. And there's also some stuff for cubic regularization method, which is another unconstrained optimization method with better complexity. So we I'm supposed to give conclusions, but conclusions are usually just repeating what you said, and everybody wants you to finish. So I'll just give that as a conclusion. It's a fortune cookie. we got on my way here, and thank you.
So I think we have time for one question. Does anyone have a question? Go ahead, Mark.
So is there a way to connect this with the complexity of it? Let's say I have t iterations and I want to choose.
Yeah, I mean, right. So this is the whole idea. That's the point. Now I want to separate the oracle requirements from the complexity analysis in a sense. Rather, I don't want to separate. I want to have oracle requirements clearly stated, complexity that comes with it, right? Oracle costs. And then, depending on what oracle I'm using, and now I can use stochastic oracle coming from the ERM, or I can have it from the finite difference approximation, or I can have it from robust gradient estimation. If they satisfy these conditions, these are the algorithms that will work with that, and this is how long it will take. Exactly.
All right. Thank the speaker again.